So let's start our last seminar of the semester. Our speaker today will be Manuela Zocali. She's a professor at PUC in Santiago, Chile, and she's also the director of the Lyrae Institute of Astrophysics, and she will talk to us about the stellar population of the galactic bulge.
Thank you very much. So before I start talking about this, let me define what I mean when I talk about bulge, because sometimes people with this word refer to a specific component of our galaxy. Instead, I, in this talk, will call bulge just the inner region of the Milky Way, all the region contained within a radius of approximately 2 kiloparsec from the galactic center. And I would exclude the central supermassive black hole and everything related to it. So the bar, for me, it's part of the bulge. It's not a different thing because it is within that region. And the reason why I am myself especially interested in the galactic bulge is because the bulge is very massive. It has a mass that is about 1/3 of the mass of the disk. But at odds with the disk, the bulge is old. It is mainly made up of old stars. And so if we want to understand how did the Milky Way form, the bulge is a good start because it is a large chunk that was in place at very early times. And so indeed, my ultimate goal is to try and unveil the formation of bulges in general by studying the only one in which we can resolve stars one by one. And the formation of bulges is still kind of a debated topic in astrophysics because there was the old paradigm that is depicted here on the left that following Kormendy and Kennigat used to think that the bulges or the things that are in the center of spiral galaxies could be divided in two big categories called pseudo bulges if they were bars, basically, if they were formed from the secular evolution of the disk, that from dynamical instability induced by the spiral arm would funnel material to the center, and where eventually it will form a bar that could thicken in a boxy peanut shape. Those kind of bulges formed in situ and supposedly over a long time were called pseudo bulges. And they were completely different. Their origin was completely different from the one of classical bulges that were thought to be merger driven. So the result of hierarchical assembly of galactic subfragments, basically things that although they were in the center of spiral galaxies, they formed in a similar way as we think that elliptical galaxies form. This was the old paradigm, but in the last years, we have been realizing that it's really too simplistic because it's not so bimodal. For instance, in our own galaxy, I hope I will convince you that we have both. We have a bar with a boxy peanut plus a spheroidal component. And the spheroidal component most likely, we are not completely sure, but most likely also formed in situ. So it's really a mix of these two things. And even if we do have a bar, so some part of the bulge certainly formed from the disk, apparently it formed very fast. So yes, an evolution from the disk, but not really secular, pretty fast. And similarly, if we look at galaxies, other spiral galaxies at high redshift, other disks, they turn out to be made of massive clumps of high star formation, as shown in this paper by Foster Schreiber 2018. And here there are some zoom in which you see that disks are very clumpy with, these are regions of high star formation, but most of them have already a bulge in place in the center. And this is about 10 giga-year ago. And so even the observation of galaxies that are forming, these galaxies that are forming now, show that the bulge is not the result of a secular evolution. It's already there at very early time. And so I said that the galactic bulge is massive and the galactic bulge is old. Let me justify these two statements. We know pretty well the stellar mass of the galactic bulge. Here I'm showing some of the recent determinations. Most of them are done by means of dynamical models that are then requested to reproduce the kinematics that is measured with observations for stars in this region. And as you can see, they range from 2 × 10⁻⁻⁻ solar masses, 1.5, 2.4, 1.8. Being astronomers, we know that the scatter among this number is not too large, but especially the scatter is not so much due to inconsistencies between one work and the other, but rather on the way different authors define the borders of the bulge that are, of course, not sharp. So that's why they are not identical. And if we, as a reference in this review, there is the mass of the disk that is more or less 4 × 10⁻⁻ solar masses. Some other quote as high as 6. But anyway, the bulge is a large fraction of it. I mean, it's not a fraction of the disk, but it is relatively large compared to that. So even if most of the mass of our galaxy is in the disk, there is another pretty large component in the center. Among those determination of the mass of the bulge, let me highlight this one by Elena Valenti, myself, a few years ago. I would like to highlight that, not only because I was involved in it, but rather because it is conceptually very different from the other. It's not the result of a dynamical model, but it is a result of counting red clump stars one by one in the VVV survey, which is a near-infrared map of the central region of our galaxy. And it has a sufficiently high spatial resolution that we could really count red clump stars in this huge region. And of course, we estimated uncompleteness that is non-negligible only in the central part, and corrected our star counts. The advantage of that is that we can then construct, we don't not only have the total stellar mass, but we can construct stellar density profiles and then consequently mass profile, because we can count star in a region of the shape that we want. So in case you want to play with this and want to count stars yourself in the way and make the use that you prefer, this large catalog in J and K, including completeness and including an estimation of the reddening in each special direction, it's available from the ESO archive, and it's described in 2 papers by Surot, Elena Valenti, and Coais. So you can download it. So I think it's important to highlight the fact that in our galaxy, and only in our galaxy, at this point, we can really separate individual stars everywhere in our bulge. So the other statement that I made is that the galactic bulge is old. And this really requires more explanation because there is less agreement in the literature. We all agree that the bulge is mainly old. And when I say old, I mean around 10 giga-year, more or less. But there is some disagreement on the exact age distribution. And I will try to resume the reason for this disagreement with the following diagram. This is a color magnitude diagram for a region of the galactic bulge obtained from the Space Telescope. This region is already decontaminated from the foreground disk that is, of course, in front of the bulge, so it's always present in the photometry. But with Space Telescope, these authors, I participated in this work, we could derive proper motions, and so we decontaminated the bulge color magnitude diagram from the disk. However, when we do that, there are some residual stars here. So in the literature, there are two groups of papers and of results. There are some people who think that these residuals here are precisely residuals of a non-perfect disk foreground decontamination and blue straggler stars. So the real bulge main sequence turn-off is only one. It's there, and it's typical of an old stellar population. Instead, there are other people that with different analysis legitimate, they conclude that these stars are instead genuine intermediate mass stars or young as 1 or 2 giga-year stars. So there is, while we all agree that the most populated turn-off is down there, we do not agree whether there is a fraction that is anyway relatively minor of stars that could be young or intermediate age, or there is none. And I quote here a lot of paper just to show that it's highly debated. There is a review by Beatrice Barbui of a few years ago that could be also read to deepen this topic. Part of the disagreement is due to the fact that the kinematic decontamination from foreground disk is not easy, because if you plot the proper motions of bulge stars, here I plot them in red, and of these stars, here I plot them in blue, they overlap largely, as you can see. And the reason why they overlap is not due to errors in the proper motion, but it is due to the intrinsically large velocity dispersion of stars in these two populations. So we cannot get a better separation between these two populations. And so the decontamination will never be perfect. Another work that is relevant on this topic is the work by the group led by Thomas Bansby and collaborator. They took spectra for main sequence stars in the bulge, actually turn-off stars, that would be too faint normally to be observed at high spectral resolution, but they were observed during a microlensing event. So when they were significantly amplified by the macrolensing, so they could be observed at very high spectral resolution. And this author determined gravity and temperature from the spectra. And from that, they derived ages and, of course, metallicities from the spectra. They concluded that the age metallicity distribution is this one that could be read in the following way, that for relatively metal poor stars in the bulge, the ages are mostly old, as you can see, older than 8 and mostly older than 10 including. But if we move to the region of metal-rich stars, the distribution of ages is flatter. And actually, there is a significant amount of stars that have between 2 and 6 or 7 giga-years. And this is really in sharp contrast with what is seen from the color magnitude diagram. So that's why there really is a disagreement in the literature. There are some other groups lately that propose a way to determine ages directly from the spectra with the strength of the CN features for the stars for which we can obtain spectra, so for stars in the upper RGB of the bulge. They also found that if we look at the fraction of stars younger than 5 gigayear, it's written up there, they see that at very high metallicity, the fraction of stars younger than 5 gigayear is not negligible, especially here, this blue line corresponds to the region very close to the mid-plane, so especially close to the plane here. So really this topic is not solved and it requires more analysis. But just to resume what I said so far, I like to have this running summary. If this is the metallicity distribution of the stars in the bulge, it's pretty broad. We could roughly divide it into a metal-rich component and a metal-poor component that here I color differently just to help you see the two components I'm talking about. And the metal-poor component is certainly only old. We all agree on that. However, for the metal-rich component, we do not agree. Some group think that this is old, but it also is a component of intermediate age, and some people think there isn't. Concerning the 3D structure of the galactic bulge, here I show an artistic picture of our galaxy seen from the top that was taken from a review of Juntai Shen and Zheng 2 years ago, just to show that there is a bar in the center. And the fact that there is a bar in the inner Milky Way is something that has been known already for some 60 years, more or less, since the work by the Vauquelin, and many more, really many more that followed. At the beginning, when we still were not able to resolve individual stars, this statement, the fact that we had a bar in the center, was based on the fact that the part of the bar that here is at the left, it's at positive longitude, it's brighter than the part of negative longitude. You see, this is not a rectangle, it's more a trapezium with this part more extended because this is the closer, the near end of the bar. Later on, we have been able, as we are now, for instance, with the BBB survey, we are able to count stars. And in particular, it is especially useful to count red clump stars, so core helium burning stars, because their magnitude is not so sensitive to age for ages larger than 1 gigayear, and it's also not so sensitive to metallicity. So they could be used as distance indicators. If they are brighter, it means that that population is closer, and if they are fainter, it's farther away. So when we observe our bulge from the sun, we see that at positive longitude, so in this plot here on the left, red clump stars are brighter, so the bulge is closer. And on this other side, red clump stars are fainter, so the bulge is farther away. It means that there is a bar, an elongated structure like this. This picture is taken from one of the most extensive work in this sense by Weg and Gerhard some years ago. The parameters, the exact parameters of this bar, so the elongation, the axis ratio, and the angle of the major axis with respect to the sun galactic center direction, here called phi, have been determined by now many times. So they are pretty robust. And some of the value are written here. The angle is more or less 27 according to the latest measurements. And this is the axis ratio. We don't need to learn them by heart. I put many papers just to transmit the fact that this is pretty robust. There is no big disagreement about this. We also know that in the outer part, the bar flares off in a structure that is sometimes called X-shape or boxy peanut, depending on the authors, but the thing is shown here. You see how it is. It's a peanut or an X, how you prefer to look at it. And this structure, the presence of this structure manifests itself with the presence of a double red clump in some specific directions, in some specific line of sight. Why we have a double red clump? Because in some specific line of sight, the line of sight crosses a first overdensity here and then a second overdensity there. And because red clump stars are distance indicator, we see a double red clump. We also know that, so this is the main bar, this is the boxy peanut or the X that we talked about, but in the outer part and in the plane, there is also a thin, long bar, pretty long. It extends up to 5 kiloparsec in each direction. And we think that all this thing, the main bar, the thin, long bar, and the boxy peanut are all part of one single structure that we know pretty well how could come in place, how could it form, because already Patsis and Athanassoula, some 20 years ago, described the fact that just by dynamical instabilities, the bar spontaneously thickened in a boxy peanut in the central part, but not in the outer part. So in the central part, the orbits that sustain the bar that are simply, at the beginning, are simply elongated ellipses in the plane, start to bend like this, to buckle and bend, so they become like that, and sustaining the boxy peanut shape. So even if it is complex, it's not mysterious. We really know that this kind of structure form from the disk, they form spontaneously just in n-body models. However, of course, that's not so simple, otherwise we would understand everything on how the bulge formed. It turns out that if we make the metallicity distribution of stars in our bulge at different positions, different height from the galactic plane, we see that this metallicity distribution is everywhere bimodal. You see, it can be fitted pretty well by two Gaussians everywhere. However, the two Gaussians, the relative area of the two Gaussians is not the same everywhere. And in particular, far away from the plane, here, this corresponds to the lowest bin, far away from the plane, metal-poor stars dominate. They make up about 70% of the total. But when we go closer to the plane, they are marginal, and the dominating component is the metal-rich. That means that, first of all, we have two components, and second, the two components do not have the same spatial distribution. One of them is more abundant far from the plane, and the other one is more abundant close to the plane. If we go even closer to the plane, we think that the metal-poor component that had almost disappeared become dominant again. But this is something that we need to explore much better, because when we get closer to the center, the interstellar extinction becomes important. And so the statistic that we have in this region is not so good as the one that we have outside. So in the same work in which myself and collaborator found that this thing is bimodal, we also managed to combine this with the spatial distribution of red clump stars. And so we could construct a map in the sky of the distribution of metal-poor stars and the distribution of the metal-rich stars. And we found that for the metal-rich stars that make up more or less 50% in total of the mass, the stellar mass, we find something that might look strange because it's really a rectangle, but it is what we expected, knowing that we have a bar. Because when we know that when we see a bar edge on, it looks like a box. That's why it's called boxy peanut. So this is what we expected. But we found that the metal-poor stars are more spheroidal. They are significantly less boxy and more concentrated in the center. So what I'm trying to say is that, yes, there is a bar whose origin we think we know already very well, but there is also another component, a more metal-poor component that it doesn't seem to be in a bar, doesn't trace a bar, but more a spheroid. Now, in this result that I'm showing you in this slide, there is a lot of analysis because we obtained spectra. From the spectra, we got this distribution. From this distribution, Now it's a bit complicated, but you could see if you are interested in my paper of the 2017, from this spectra combining this with the density distribution of red clump stars, we derived these maps that are artificially symmetric because we imposed fourfold symmetry. So we all might think that there is a lot of analysis that could be wrong, right? So it's not a direct measurements. However, recently there was another work that concluded the same thing much more directly. And it is this work by Lim et al. 2020. It is a result of a survey of the galactic bulge in the optical with the DECAM camera at the Blanco telescope. So I'm trying to, this view graph is really dense, but I'm trying to walk you through the result. They have photometry only. However, they found here in this plot that the U minus I color correlates pretty well with metallicity for many stars that they have in common with the spectroscopic work I was talking about before. You see, so the U minus I color is a pretty good indicator of metallicity. And they know even how to calibrate it. So once they determined that, they went and plot the color magnitude diagram for red clump stars using U minus I as a color. And here what you are seeing, all these boxes are this region of the color magnitude diagram, but in U minus I versus K as a magnitude. And we are seeing the contours. Here there are 9 panels. The 9 panels correspond to 9 different line of sight in our bulge. What are we seeing in these plots? That we see a bimodality in color, which, thanks to this plot, means a bimodality in metallicity. So there is a metal-rich blob, a metal-rich component, and a metal-poor component. Let us look at the metal-rich component, the red thing here. The red clump for the metal-rich component is brighter here. So here it's brighter. And on this other side is fainter, and in the middle is double. So we are seeing here the bar, the fact that here is brighter and here is fainter, and the boxy peanut or the X shape, because in the middle is double. We see this at every 8 from the galactic plane. Brighter here, fainter here, double there. However, the metal poor component is everywhere at the same magnitude. You see, let me highlight that the metal poor component here highlighted in blue, it's always at the same magnitude roughly. Doesn't change so clearly as it does the metal rich. So what does this mean is that the metal rich component is a bar and the metal poor is more spheroidal. This is a more direct result because there is not a lot of analysis, just photometry of red clump stars. So to keep fixing the things that we've seen so far, the metal poor component is only old. Instead, the metal rich is old and maybe also with a young component, and the metal poor component is a spheroidal, while the metal rich is a bar plus a boxy peanut. What is the kinematics of these two components? Many people measure the kinematics. For the metal poor stars, we see rotation. The different colors are different 8 from the plane, different latitude, but they are more or less similar. However, the metal rich component also rotates a bit faster, it would seem. You see that the slope here, that is velocity, radial velocity versus longitude in both plots, seems to be a bit steeper for metal rich star than it is for metal poor stars. So perhaps the metal rich component rotates faster than the metal poor, but it's not dramatic. However, in the velocity dispersion, the difference is more clear. The velocity dispersion is more or less constant for metal poor stars at different longitude and at different latitude. Instead, for the metal rich stars, there is a pretty large gradient, with the velocity dispersion being lower far from the plane and higher when we get closer to the plane. Many different authors find the same. So this is also not debated. And what about models? It would seem that here the points are the data and the curves are models from De Battista et al. Models are able to reproduce, at least qualitatively, the same behavior for, this will be the equivalent of metal-rich stars. In these models in particular, yeah, they don't have metallicity, they have ages. So this will be the relatively younger component in the model, and this will be the relatively older component that supposedly should correspond to the metal poor ones. Here no gradient, and here more gradient. We could see rotation even not only with radial velocities, but also with proper motions. And it's particularly interesting, I think, this paper by Clarkson et al. From the data, the space telescope data that I have shown even before when talking about the ages, they had proper motions. So what they did is by using some photometric indices developed by Brown before, here the indexes are a combination of optical and near infrared photometry, but it was demonstrated that they correlate with temperature and metallicity. So you could use those indices to separate the metal-rich component from the metal poor component. And if they plot the proper motion in longitude, so the transverse velocity versus the distance of those stars, they also see that the metal poor component rotates slower than the metal-rich component. So in other words, we all agree, and so we could write it in our summary, that the metal poor component rotates slower, a little bit slower. It's not devoid of rotation, while the metal-rich star rotates faster, and the metal poor star has a constant velocity dispersion, while the metal-rich star has a gradient in velocity dispersion. There is another property that we can explore, and it's the alpha over iron ratio for this population. Many different authors explored that, but I will show you what I consider the best, the more clear result about this, which is by Queiroz et al. From APOGEE combined to Gaia data. APOGEE gives the chemical abundances, and Gaia the distance and the proper motion, although here they are using only the distance. So what they find here is the alpha over iron ratio in 3 different cylinders that I draw there just to help you find them. This below, it corresponds to the region closer to the center, and here we are moving up, so farther away from the plane. They found that in this plot, the stars behave bimodally as a difference. So far everywhere is bimodal, so that's not strange. There is the metal poor component that is alpha enhanced, and the metal rich component that is not alpha enhanced, but also the metal rich component dominates close to the plane, and when we go far to the plane, the metal poor component dominates. So it is the same result that other people found before, except that now we see very well that it is bimodal in the alpha over iron ratio, meaning that the metal poor stars formed quicker, so with a higher star formation rate than the metal rich stars. And this behavior is everywhere in our galaxy, actually. Here there are larger cylinders that show the same thing with higher statistic, because as we make the cylinder higher, you have more and more stars. So the metal rich solar scale dominates in the plane, and when we go out, the metal poor component alpha enhanced dominates. The fact that this thing is double everywhere, it's strange in a sense, because we know that even in the disk, we have the thick disk that is alpha enhanced, and it's farther away from the plane, has a larger height scale. and the thin disk that is not alpha-enhanced and it concentrated in the plane. So it almost looks like our galaxy is two galaxies, really two groups of stars with different star formation rates. So they were different from the beginning. How can we explain this, that in our galaxy there are stars of two types? De Battista et al. And Clark et al. From the same group, Clark is a postdoc of Victor de Battista. They proposed a scenario that makes sense to me. It seems very plausible, and it's that the stars that are alpha-enhanced are those that formed in clumps at early epochs. Instead, the stars that are not alpha-enhanced, so the one that are lower, that dominate in the plane, the metal-rich component, are those that formed far from the clumps. These are the models, and these are the data from APOGEE. Here they are both dominated by the low alpha stars because they are analyzing in this figure the stars closer to the center of the galaxy. And so basically this model is more or less compatible with the finding for these galaxies at high redshift. We do see that the star formation is bimodal in a sense. There are stars that form in this high star formation rate clumps and other stars that are formed outside them. So it's not unreasonable to me that we have these two components in our galaxy everywhere, because eventually those clumps dissolves. But we can have stars in our galaxy that form either in the clumps or outside the clumps. And that's why this distribution is so bimodal with nothing in between. I think it deserves some faith. It could be some more exploration, of course, to be able to understand why they end up in different positions in the galaxy. So if we keep going with our summary, the metal poor stars have high alpha and the metal rich stars have also low alpha. So these two components are different in many respects. Can we conclude that they have a different origin? So they are, maybe this is the pseudo bulge and this is the classical bulge. And not really, because apparently both of them could be formed in situ, as I just mentioned. This may be in clumps and these outside clumps. Still, the modelists say that they can construct models of our galaxy, self-consistent models in cosmological context that end up with two disks, one that eventually is the thin disk that is colder, so it has a smaller velocity dispersion. This disk ends up with a bar and the marked boxy peanut. Instead, there is another disk that is radially hotter, so with a larger dispersion, and this disk would eventually form also a bar, but less elongated, weaker, and so vertically thicker. So models could reproduce, at least qualitatively, a more spheroidal component, in other words, formed from the thick disk, and the more elongated bar with the boxy peanut formed from the thin disk. Other groups from completely different models, Francesca Fragudi and Paola Di Matteo, find the same result. The metal poor comes a bit rounder than the metal rich, but they are both formed in situ. So in other words, we do have two components, but we cannot conclude yet that the spheroidal component formed as a classical bulge from merging of external fragments. Maybe it might. I think we cannot exclude that, but it could also form in situ. So this is my summary, but before I conclude completely, I want to mention what I think are the direction of the future work, at least in my group. There are a few open issues. One that I already mentioned is what is the age distribution of the metal-rich stars. We should address that with more data. Also, another open issue is that we lack a proper characterization of the 3D structure of the metal poor spheroid. We know that metal poor stars are not in a bar, are in a more spheroidal component, but while for the bar, we know the angle, we know the pattern speed, we know the axis ratio. For the spheroid, we really don't know much. Okay, it's rounder, but what is the density distribution? We don't know much because up to now, the density profile, etc., are of the two components together, not really separate. Another open issue is that concern the RR Lyrae. I will spend a few more minutes on that because the RR Lyrae are a pure old population. You can only form RR Lyrae in populations older than 10 gigayear. So that's a great advantage if we want to reconstruct the early formation for this galactic component, because here we have kind of fossils, something that was there at the beginning. So because later on we have two populations with different properties everywhere, what about the first one? I think it's an interesting question to investigate whether RR Lyrae trace the same 3D structure as metal poor stars. The RR Lyrae are a poor old population, but their metallicity distribution is more metal poor than those that we have been talking about so far. So there, I had to draw them because I didn't have them to plot in the same scale, but more or less the peak of the metallicity for RR Lyrae is at -1, -1.5, more or less. So they are more metal poor than the metal poor stars that we have been talking about so far. And they are also older. So, however, they could trace the same population as this one, because it could be that within this population of metal poor stars, only the metal poor tail is the one that may eventually form RR Lyrae. In order to form RR Lyrae, you need stars that burn helium in their core on the blue or on the relative blue, so blue enough to cross the instability strip. So it could be, here the vertical normalization is just arbitrary by me, just to make it visible. Of course, there are a low number of RR Lyrae compared to red clamp stars. So it could be that only those in this tail are blue enough, while in the horizontal branch, to pulsate as an RR Lyrae. It could be then that this is just that this RR Lyrae and the metal poor red clamp trace the same population, so the spheroid. Then it's relevant to investigate what is the 3D distribution and what is the kinematics of RR Lyrae. In the literature, this topic is highly debated. There are people that say, yes, the RR Lyrae trace a spheroid. So it's the same population as this. And then there is the bar that is only metal poor. But other authors say that RR Lyrae, that are, by the way, very good distance indicators, so in principle should allow us to trace the 3D structure very well, they trace as a bar. And some in the middle that say yes and no. I will expand on this. But this scenario, it's very strange because they say, of course, with evidence, they say that the oldest stars are trace a bar, and then there are stars that are more metal rich, probably a bit younger, that trace a spheroid, and then those ones trace a bar again. I think that to imagine a scenario in which this is true is going to be really difficult. But if this is what observations say, we will have to cope with that. But let us try to agree before on what the observations say. So Carlos Quesada, my PhD student, is analyzing a catalog of arar Lyrae that we find from VVV data in the central region of the Milky Way. This is something new because so far the survey, the catalogs available for variable stars in the bulge came from APOGEE. That, because it's optical, doesn't get to the midplane because of the large extinction. Instead, the near-infrared VVV data allowed us to map all this region. It took quite a few years to classify properly the many variables that are present in this region to get a sample of pure arar Lyrae. And we are currently analyzing their distribution in the plane. The sun here would be there, and this is the cone that we see toward the bulge. These are some preliminary contour for the distribution we see. We don't know, it's not completely circular. It's certainly elongated, but not as elongated as the bar. So we are trying to derive parameters for that. It's work in progress. We are also analyzing the rotation of the stars. We can analyze the rotation of those stars because we have proper motions, but it's not done yet. So far, we can analyze the rotations from those ogle arar Lyrae that have been observed by APOGEE. So we have spectra, we have radio velocities, and the result is also puzzling because the stars that are closer, we have orbits for that. I skipped something that it's important. We have orbits for that because we have proper motions from Gaia and radial velocity from APOGEE. So the three components. We could derive the orbits, and if we select the stars that are in inner orbits, so with apocenter that keeps them all the time in the bulge, they do not rotate. Instead, if we take stars that are on larger orbits, sometimes get out of the bulge, they do rotate. This is very strange, but this is the same thing that Andrea Kunder finds from Brava data. So this adds a new level of complication. Even the arar Lyrae seems to be bimodal, seems to have a more concentrated component that seems to be completely spheroidal without a rotation. And another component that with a larger rotation, the interpretation of this, I think, is going to take a little bit longer. And maybe I should, let me conclude with this, that we are trying to, I would like to mention that we are trying to focus our attention on the nuclear bulge right now, on the thing that is inside the two innermost degrees of our bulge. It's called the nuclear stellar disk. This is, in my opinion, the two most interesting degrees of our galaxy, because there is everything in here, even excluding the black hole, because we study stellar populations, and I think we are not an expert on the dynamical issues related and the high energy issue related with the black hole. But even excluding that, here there is a nuclear stellar disk. There is the central molecular zone that is a disk very dense in molecular clouds and star formation. And there are young massive clusters. So really, there is everything. There is a lot going on. And the data that we have are starting to be good enough. The instruments that we have are starting to be good enough to explore that. For the moment, we have in our hands, in my group, proper motions from VVV. Notice that Gaia do not get there because Gaia is an optical instrument, so doesn't have proper motions very close to the plane. And we do detect the disk. This is medium proper motion in longitude. So we see that there is a component that really it's different from the rest, and it's a cold component, as we can see in the velocity dispersion. You see it's very low dispersion in proper motion in both axes. So our future plans are to study this more in detail in proper motions and also in photometry with new data that we have with OCAI. If you are interested on that, you can ask me a bit. I think right now I'd rather conclude. So with the thing I mentioned before, and also we would like to understand how does the nuclear bulge and the central molecular zone fit in all our picture, incomplete, but at least some picture for the formation of the galactic bulge. And with this, I thank you, and I'm happy to answer questions if you have.
Okay.
Thank you.
Thank you, Manuela. So now we open for questions. Anyone? Rodrigo? Can you hear him, Manuel?
Yes, I think so.
Maybe it's a basic question, but I was wondering if you can estimate the amount of mass that is in the bulge that came from dwarf accreted galaxies or minor mergers.
Not really, because we cannot tell. We cannot tell which stars came from accretion events. We don't see clearly stars that stick out as accreted. We see a bimodal distribution in here, for instance. Let me go back to one of those here. We don't see something that, for instance, is metal poor with low alpha, clearly that could be accreted. Maybe there are a few stars there, but they are really a few. And so accreted from dwarfs at later time that should locate here, we don't see anything. Maybe those stars come from very early accretion of dwarfs that formed their stars at very early time. So basically, if this is a classical bulge that came from mergers, we don't know yet. May or may not at the moment. So really, we don't know.
Thank you.
You're welcome.
Okay. Anyone else? I have a question. I was curious about the scenario, the clumpy scenario. As far as I understood, the spherical component is mostly metal poor. So
yes.
But you said that the metal poor component they are formed mostly outside the clumps, right?
No. These will be the stars that are formed in the clumps because they are enriched in alpha elements. So they must have formed in a region with a very high star formation rate.
Okay, in the clumps. Okay, so I understood it. It was wrong. Okay. And okay.
So this paper was submitted by the Batista et al. Stay tuned. Maybe it is accepted.
It's already on archive?
No.
Not yet. Okay, this is interesting.
There is a paper by Clark et al. That proposes a similar scenario for the stars in the disk. The logic is the same, but in the Batista, the things are a bit more specific for the bulge. The main idea is already here.
Okay, anyone else? Alan?
So I'm wondering if there's any efforts ongoing to try to use some kind of Milky Way progenitors at higher redshifts. You showed like a plot from redshift 2, but maybe observations at redshift 3 or 4 can help, because I was wondering that maybe a burst of star formation around redshift 4 or 3 could explain these old metal poor stars with little rotation. because the velocity dispersion of the gas declines with time, right? So if you form them very fast, very early, you get kind of an asteroid with little rotation.
Yes, I don't know about any effort in that direction. I can only mention that these models by De Battiste et al. And Fragudi are inserted in a cosmological context. So they get a cosmological simulation in which they don't have enough resolution for a single galaxy, but they select galaxies that eventually look like the Milky Way. They track them back at very high redshift and they increase the resolution there, and then they follow them back. That's the logic of these models. This is all I know. In the end, these models analyze the resulting galaxy and compare it with the data. I don't think they really trace back the stars that were formed at redshift 3 or 4. Maybe they could, but I haven't seen it discussed. I don't do it myself, and I haven't seen this part discussed in their papers.
Questions? I have the last one.
Yeah.
Is there any effort to look at local spiral galaxies and the bulge of local spiral galaxies to compare and try to find other clues, other similarities with?
Yes, there is this survey that is called Timer, led by Dimitri Gadotti and Francesca Frangudi. They are trying to do that. So just to compare with other local galaxies. So results from that are coming out more or less now. I didn't go in detail right now, but I think that is the project to pay attention to when the result start coming out.
So they don't know yet if the central region of our galaxy is normal compared to other spiral galaxies, or it's typical, or?
Yeah, no, I don't think so. Yeah, but we should stay tuned to that result. These are Francesca Frangudi and Gadotti are the ones the paper to pay attention to. About the previous question, also there is this paper by them 2 years ago in which they follow Milky Way-like galaxies in cosmological simulation. It doesn't answer directly your question, but by finding stars that end up very similar to the Milky Way, they conclude that they formed the stars mostly in situ. So not a significant accreted component. Yeah.
Okay, so I think on Zoom, does anyone have a question?
I have a question. Can I?
Yeah.
Okay.
Hello.
So, hi. In that plot that you showed the star formation rate with the mass, can you get back to that?
The star formation rate with the mass.
Yeah, in redshift 2, I think.
This. Yes.
Yeah, this one. Yeah. So, does it apply to the Milky Way too? Because in that plot from Ana Queiroz, that has the alpha over iron higher in some region, it also shows a higher
star formation rate.
Yeah. So it's more massive too than the other clump or not in that work?
I mean, our galaxy would be like there more or less, but of course we cannot observe our galaxy at redshift 2, so we cannot put it here. But yeah, it makes sense with the plot of Queiroz that those stars would be the one formed in the clumps, no? And those would be formed outside the clumps. except that we don't really know where the stars formed. We know where they are today, but we have no way for them to trace where did they form.
Okay.
So it's a complicated comparison. We can, for sure, those formed in a region that has a higher star formation rate. But
Okay.
where was this region? This at the moment, we don't know. It's not so easy to track it back.
Okay. And there is something about this group be more massive than the other, or?
No, because those are individual stars everywhere here. So we don't know whether these formed in a more massive clumps in these in the field. They are now spread everywhere in the field. What we do know is that right now these two components make up more or less half of the mass of our bulge. More or less half of the mass is included in this component and another half in this other component. But they are both spread everywhere.
Understand. Thank you.
Welcome.
Okay, more questions? So I think we can thank Manuela again for the excellent talk.
Thank you.
Okay, I'm going to stop transmission. And okay,